This is the 7th video in our 10-part series on quantum computing. I'm Prof. Priya, and today we'll explore Shor's algorithm, the quantum algorithm that threatens modern cryptography.
Professor, in our last video, we learned about Grover's algorithm for searching. How does today's topic connect to that?
Great question, Sneha. Today we'll learn about the Quantum Fourier Transform, or QFT. It's a linear transformation that maps quantum states into their frequency domain, just like the classical Fourier transform, but for quantum states.
Professor, when you say frequency domain, what does that mean for quantum states? How is this different from the classical Fourier transform?
Excellent question, Arjun. The QFT takes a quantum superposition and transforms it to reveal hidden periodicities. Watch as we apply QFT to a superposition state. See how it extracts the underlying frequency patterns. Now let's tackle the main problem Shor's algorithm solves, factoring large integers. Given a number n, we want to find its prime factors p and q, such that n equals p times q.
This sounds straightforward. Can't we just try dividing by all possible numbers until we find the factors?
That's the key insight, Sneha. For small numbers, yes. But for cryptographic numbers with 1024 bits, you'd need about 2 to the power of 512 operations. That would take longer than the age of the universe. Here's how Shor's algorithm works. Step 1. We prepare a quantum superposition of all possible input states from 0 to 2n minus 1. This gives us quantum parallelism across all possible inputs.
Ah, I see. This is like Grover's algorithm where we work on all possible states simultaneously using quantum superposition, right?
Exactly right, Arjun. Step 2. We apply modular exponentiation, computing a to the power of x modulo n for all x values simultaneously. This creates a periodic function that's key to finding factors. Step 3 is where the magic happens. We apply the Quantum Fourier Transform to extract the period of our modular exponentiation function. The QFT reveals this hidden periodicity efficiently.
Professor, I understand we find the period, but how does knowing the period help us actually find the factors of n?
Great question, Sneha. Step 4. Once we have the period r, we can compute the greatest common divisor of a to the power of r by 2 plus or minus 1 with n. This mathematical relationship gives us the factors. Here's the revolutionary part. Shor's algorithm runs in polynomial time, specifically polynomial in log n. Compare this to classical algorithms that require exponential time. This is a dramatic speedup.
Wait, does this mean Shor's algorithm can break RSA encryption that protects all our online banking and shopping?
Exactly, Arjun. RSA encryption's security depends entirely on the difficulty of factoring large numbers. A sufficiently large quantum computer running Shor's algorithm could break RSA encryption, threatening much of our current digital security.
This sounds scary. Are quantum computers powerful enough to break RSA right now? Should we be worried about our online security today?
Good question, Sneha. Current quantum computers aren't quite there yet. To break RSA 2048, we'd need about 4,000 logical qubits, but today's systems have around 100 physical qubits with high error rates. Let's summarize. The Quantum Fourier Transform is the quantum analog of the classical Fourier transform. Shor's algorithm uses QFT for efficient period finding, making integer factoring polynomial time and threatening current cryptography.
This is fascinating but also concerning. How can we protect our communications against quantum attacks? Is there hope for maintaining security?
Excellent question, Arjun. Next, we'll discuss quantum error correction and how to combat noise in real quantum systems. We'll also explore post-quantum cryptography that can resist quantum attacks. Thanks for joining us.